Our next speaker is Peter Washington. He is a graduate student in bioengineering systems medicine and has MCHRI support in the form of a Spark Award.
So hi everyone, I'm a third-year PhD student and I study autism. And so the power of studying autism is manyfold. First and foremost, it's useful for treating autism, but kind of stepping big picture. And I'm starting with this because if we run out of time, we could skip the big picture. It's a very heterogeneous phenotype. And so, for example, you might have one child who has trouble making eye contact and also trouble with hand stimming and has autism, and you might have another child who doesn't have any of those problems but has a speech delay and has some other issues, and they're also diagnosed with autism. And so it's such a highly heterogeneous condition that's very well ill understood that we can learn a lot about kind of all of child neuropsychiatry by studying it. And similarly and perhaps relatedly, it's a complex polygenic condition, and so by learning about autism, we can learn about maybe, a lot of other disorders as well. And so we're taking a data-driven approach to understanding and treating autism. And so starting with the screening methods, we took a clinical questionnaire called the Social Responsiveness Scale that's used to, it's a parent-directed questionnaire that's used to screen for autism. And we applied a machine learning technique, so this is the beginning of the machine learning AI as part of the talks, on the parent questions, answers to these questions. And we applied 3 different feature selection paradigms to these questions. We applied mutual information, which is a measure of how much does an answer correlate with the final outcome, so autism or not. It's looked at independently of the other questions. We also looked at some other techniques. So RFE stands for recursive feature elimination. What's interesting and different about this technique is that once you choose one question, and then you can try it again for a second question. That second question in the ranked list that you get is going to be independent of the first question, whereas in mutual information, it doesn't take into account these correlations between questions. And what's interesting and what we see here is that relating to peers always shows up as the most predictive question for autism, but we also find that trouble keeping up with conversational flow, it's highly correlated with relating to peers because it doesn't show up in this ranked list of our recursive feature elimination. And so we can use this technique in general, not just for the SRS, but for other questionnaires to find what are the most predictive questions. Similarly, we apply this technique again for not the SRS-derived autism diagnosis, but the autism diagnosis as derived from a cocktail of clinician questionnaires because different clinicians prefer different questionnaires. And what's really interesting is that if we just take the first question, the most predictive question, and we feed that into a machine learning classifier, namely a neural network, because that's what people like these days, we find that we get higher than 90% AUC precision and recall just from that one question about keeping up with conversational flow. And as we add more questions to that list and apply it to the machine learning classifier, the benefit is marginal, but you kind of get this logistic taper. The results, interestingly, go down when we don't predict the SRS-derived diagnosis, but instead the clinician-derived diagnosis, which could be from a variety of different measures, which tells us that the prediction of autism as characterized by the SRS is different from those of other measures, such as ADOS or ADIR. So SRS is capturing different aspects of socialness and of behavior than these other clinical measures, which are all used to diagnose and screen for autism. So this has kind of big implications, actually, for what questionnaires clinicians choose to administer. So we know that we can identify the top behavioral questions, and they can be used to predict autism without the whole questionnaire, just a small subset. Kind of a related question is how can we model autism in a way that's quantitative, which it's not really right now, and interpretable. And actually a secondary benefit of this is there's a lot of talk about privacy these days. And if you reduce the dimension of all of the questions, you have a representation of the data which could perhaps be shareable with the public and used for machine learning. So here we have a picture of a denoising autoencoder, which is a neural network that can be used for reducing the dimensions of things, in this case, the SRS questions. And here's where things really get interesting. When you reduce things down to only one dimension and feed that single dimensional representation to these neural network classifiers, you get basically perfect performance with that single dimension, whether you use a linear dimension reduction technique like PCA, which we all know, or a nonlinear technique such as TISNE or autoencoder. So in this table, it's predicting the autism diagnosis as defined by the SRS, and you would kind of expect that even if you reduce that down to one dimension, it's going to be pretty perfect. But when you go to the clinician-derived diagnoses, which can be, DSRS or many other questionnaires, ADIR, ADOS, whatever, we find that the denoising autoencoder, which is a nonlinear technique and which does not require any hyperparameter optimization, significantly outperforms the linear technique and the technique that requires a lot of optimization, which we did not do. And therefore, we learned two things. On the method side, we learned that in terms of nonlinear dimension reduction, denoising autoencoders are a much more efficient and easier method to use. And in terms of modeling the autism behavior space, we learned that autism is at least slightly nonlinear with respect only to the SRS. We can't say the same yet about ADOS or ADIR. And you could also visualize this very nicely, and it's clear that on the left side, there's a clear linearly separating boundary. On the right side, it's not so much. So great, we know that if we get these questions, we can predict autism, but how do we do this at scale? And so we can turn to crowdsourcing, and we did do this. We put a bunch of videos of children with autism on Amazon Mechanical Turk, and we had them label these behavioral features that are used in these questionnaires, or at least versions of them that are derived from them. And what we find is that, and we also had expert clinicians do this, and what we find is that the average deviation from these clinician ratings is not too far. We get this nice distribution where most of the answers are between this 0 and 1 categorical ordinal difference from the clinician, which is the difference between sometimes and often, or often and always, which for any one particular question is not actually that big of a deal for deviating. We did characterize in the paper the tail of this distribution. It turned out the reason for those were the questions themselves. They were compound questions, which clinicians might be better at answering than people in the crowd. It was asking them to do like 20 things. So it wasn't specific to the video. The tail there, when it deviates, was from the questions. We also tried gamification, and that didn't work quite as well as crowdsourcing in a paid manner. So how do we convince, I have 30 seconds, so just to go really fast, how do we convince parents to share the video with us? We can apply privacy-preserving mechanisms, we can run machine learning, and we can find that the classifier performance doesn't really go down. And I said I would talk about treatment. Long story short is that it helps with treatment as well. So thank you, and I'll take questions.
Okay, no one else is lined up, so I will go ahead and ask a question. So you mentioned at the beginning that things we can learn from autism may be applicable to a lot of other diseases in the population. And I was wondering, what are some of the most obvious next targets to use your techniques to apply to better understanding other diseases?
Yeah, so a big one is ADHD, where there's, SRS can be used to quantify that as well. A lot of these other established clinician questionnaires cover these as well. So I think in terms of the questionnaire space, it would be a lot of the anxiety, ADHD, OCD space. I think in terms of when we start to look towards the genetics and the polygenic nature of autism, Parkinson's and schizophrenia gets interesting as well.
Peter, you're going to put me out of business as a child psychiatrist pretty soon. My question to you is, can you just say 2 words or 2 minutes about what it is that the treatment applications would be for this approach?
Yes, so this will not put any clinicians out of business. What it's going to do is help clinicians see more patients and therefore, help more people in a very efficient and scalable manner. So we're not trying to put any clinicians out. We're trying to help clinicians and help the children with autism. Thank you.